today, our main topic is BWT. In fact, if we can finish BWT by the end of today, we are ahead of schedule. So I think we can finish it by the end of today, plus talk a little bit about pattern matching, as in search. In case you didn't have enough bananas from last week, so we just try to refresh your mind. There's a few questions that people asked me after the lecture last week, so I thought it's good to recap those questions and answer again. Number one of the questions they asked me is like, in order for BWT to be useful, does it mean that we need to have a unique character somewhere in the string to identify that a banana has to be start with hash or end with hash or something? For now, yes. But 2 lectures later, you'll find that no, you don't. But for now, because something that I can't go through it now, it has to discuss maybe 1 or 2 lectures later. It's a bit more advanced. For now, you assume that there'll be one symbol in the string that you can uniquely identify. That's the one that I want. In case like your answer somewhere is hidden in one of the rows here, you know which one is the answer. Then the one start with hash is the one that you want, for example. So there got to be a marker in the string that you know which one is the string that you want, because these are all the rotations. Means like, although they are the same string, they start with a different position of the same string, but you need to know which one is the original string. So now we assume that you either mark it at the beginning with a special character or at the end with a special character, so you know which one is the string. But as I said, 2 weeks later, you'll find that it doesn't really matter. But for now, assume that it matters, okay? And last time, if you remember how we do the BWT, again, the characteristic of the BWT is like it can somehow group all the same letters together, more or less together. For example, all the A's together, all the N together, hopefully. And the transformation is ridiculously simple. So you get all the rotations, you sort them, you sort all the rows, and the last column is your BWT. Now, we also said that if anyone, I guess this year you guys look a bit more normal. In the past, there was one student who actually did it at home. I was quite impressed. Tried to find all the rotation of this string and actually sort it with papers. It's not sorted by computer program. I've seen papers. And managed to get the last column. So I tell you that it works. So to do the transformation to get to the second line is relatively easy. It's really 2 slides. It's all the rotations. Sort them, get the last column. Now to decode it back to the original string, it's not complicated, but it's tedious because you need to, put the encoded string here, and then sort the encoded string, add the encoded string again in front, sort them again, add it again in front, sort it again, add it again in front, sort it again, add it in front, sort it again, add it in front, sort it again. You can slowly see the banana appears. So add it in front, sort it again, add it in front, sort it again. And then, as I said, you'll find it is right here. Now, to memorize these steps are not hard. But in fact, when you're doing it, it's very tedious and very expensive because it involves you concatenate the encoder string in front, sort it. You can't sort it in one go. You sort it and add it again, sort it and add it again. So you need to sort many times. So it clearly is not the most efficient way to do that. And when the string's getting longer, even one of you guys asked, do we need to represent actually the whole matrix? No. Because each row here is the same string, it's just a different starting position. So you can represent each row by the different starting position. That's it. So it's not lots of space here, but it's the operation-wise is expensive because you need to do the sort many times. How many times? As many as the length of the string. And that is really, really slow. So now this answer, the question is like, do we need to encode the whole table, whole matrix? No, a single pointer for each row is needed because just the different starting offset position of the string. This is just a summary of the algorithm because you guys like to have the algorithm somehow. Although it's quite easy, but this is what it is. So just like get table contain the rows of all the possible rotation, sort the rows, then the last column output it. That's the encoding. The inverse is repeat it, add it in front, sort it, add it in front, sort it, add it in front, and then at the end you will find that the one with the special symbol, maybe hash in front, for example, is the one that you want. Now, before I'm going to talk about a more efficient way to decode it, because that way to decode it is just not practical. It is too slow. Before I'm going to talk about that, I talk about once you get into the BWT, what else you can do to make it compress. Now, as I said again, BWT is not a compression. It transforms the string of 200 characters becomes another string of 200 characters. It's not larger, but it's not smaller. It just tries to transform it such that same characters are likely to be next to each other. And by doing that, you know that you can use your famous running encoding. That is even simple, but running encoding plus BWT will give you a mouse to run. You can compress things really smaller. So, but before that, there's also some other technique we can use to bring the entropy smaller, but reduce the entropy. So how are you going to do that? One of them is also very simple. It's not running encoding, but it's as simple. It's called move to front. And literally, the name itself, they name it really, really good because that's the whole idea, move to front. So suppose that you have a symbol A, B, A, B, A, C, A, D. Instead of represent this sequence of strings using the ASCII representation, there will be 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. We try to represent it using a smaller value. How are we going to do that? We assume the whole ASCII table, they're queuing up like a queue from 0 to 255. It queue up sequentially. When we are going to, so let's say we simplify. In this example, we simplify it a bit. We assume that it's not 255 symbols. Assume only like, I don't know, 26 alphabets from A to Z. They queue up from A to Z. So the first one is A, second one is B, and so on. And we assume that the index is 0 base. So the first one is the position 0, second one is the position 1, and then 2, and so on. So when we refer to A, it means the position of A in the queue is at the position 0. And after we refer to A, after the symbol being referenced once, we move that symbol in the front of the queue to jump to the front. So after A has been referred, we move A into the front. But A was the front first, but still the front. Then the second symbol we refer to is B. B was in position 1. 0, 1 was in position 1. But after we reference B, we move B to position 0. It jumped to the front of the queue, moved to front. So then now A is no longer in position 0. It becomes 1. So then you refer to A. A will be position 1. But after 1, you move back to 0. So it becomes 0. Now the idea of doing that is like, if I have a symbol, say Z, 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 The first time I revert to that is 25, because 0 base, 26, okay. But the second time I will refer to it is 0, because I move it to the front. So the idea by doing that is that if you have a symbol, even 255, whatever, even they're very bad at the 255. But if you refer them often enough, their value will be brought down to a smaller value, because they will move closer to the front of the queue. So this move to front is a simple idea in a sense that, like, if I have a consecutive symbol, like A appear many times, except the first time, the rest of it will be 0. So it means like if you use that with the BWT, there will be lots of 0 in the file. Are you with me? Yes.
So 0 only appears when a letter is repeated many times without any other letters in the middle, right? Because
yes,
any new will move it to 1.
Yes, correct.
So then you have a bunch of 1s inside of many 0s.
Correct. But still, from the entropy point of view, a lower value is still better than a higher value.
Oh.
So as far as, like, for example, as I said, like, you may have a value before that is like, you know, in the ASCII maybe 112, but after you move back to the front is 0, but later it's not reversed, so being like, I don't know, pushed backward, but still it will be a lower value.
Well, you still need 8 bits, right?
It still need 8 bits if you have a fixed length representation. If you don't have a fixed length representation, later we'll discuss, if you have a variable length representation, it's a different story. So, anyway, imagine that if you're going to build a program, if all the values are high values and the variance are very high, there's not much optimization you can do. But if all the values are similar value and it's a low value, it's much easier to optimize that. So we always like to bring down to a low value. But in particular, in this case, because the BWT, we have lots of same character consecutively. You can do running encoding because it repeats many times. Or naturally, if you do move to front, sometimes as good as the run length because they're all 0.
But like, even say there's like 200 zeros, that's still longer than a 0 followed by number 200. Right?
Of course, of course. So what I'm trying to say is that if you have a file of, say, 200 zeros, versus sometimes it's like, I don't know, 1, 2, 3, 4, or like a value change and so on. You try to do a gzip or some other compression on it. The 0 is much easier to compress. You'll get better compression ratio. When the value is lower, the entropy is lower, you will get better compression value. Okay? Now, keep your questions first. Then somehow I feel like I lost a slide. That it should be there, but it's not there. So let me go to the previous lecture. Yeah, I lost a slide. So let's do this one. So now, this is one I wanted to show. A normal commercial compressor, they never use one technique. It's always a combination of techniques together. So consider if you're doing a normal zip software. In the old day, it's called PK zip. But right now, if you're doing WinZip or many commercial zip software, they are still mostly based on LZW. You know it already. It's a dictionary-based compression. Now, if you're going to use another compression, such as bzip2, which is quite popular these days, if you are more like a geek, you will do bzip2, because it gives you a better compression ratio. Now, if you look at the bzip2 inside, mostly they're the combination of first, do the BWT, So you bring all the similar characters or same characters together. Do the running encoding. Do the move to fun. Then, finally, do the arithmetic coding. You will get probably the best compression ratio you can get with all the technique you learn in these 2 weeks. I always think of like making an assignment like that because you guys will have tremendous satisfaction because you will find that my assignment is doing a commercial compressor. It is. Except that I don't know how to mark plagiarism because none of you guys will do it by yourself. It's just a combination of existing library. Like one is BWT, one is RLE, one is move to fun, one is AC. You probably like, if you copy different library in a different order, you get a different compression ratio. That's about it. The only thing you learn is like, is order important? I mean, of course, if you are not smart enough, you may say, let's do running encoding first, then do BWT. That is just like a waste of BWT, for example. So clearly, they're order dependent. So those things, when I say plus, don't swap the order. If you do AC first or something like that, you just ruin everything. They have to be in this order. You get the best out of each of their characteristics. But what I'm trying to say in this slide is I don't want to point out this particular example. I just want to say that the techniques you learn, why we need to cover different techniques, because practically speaking, you just don't use one technique. You use a combination of them. But each of them have to use in some certain way to get the best out of it. All right. So, yeah. So if you guys just want to build a compressor, that's probably better than, I don't know, zip or something, or build a better JPEG or GIF. In terms of the compression techniques, you are more than capable of doing that, just with so far the techniques you learn. Even you want to use a newer compression technique or algorithm we haven't covered, they will be fall into one of the type that we cover. It's a matter of like you adapt to the new algorithm of the same type, you should be able to know how to play around with that. Okay. Now then, come back to today's lecture. That was from last week. Content. All right. That will be this one. Okay. So we quickly discussed this move to fun idea. I also put the original paper of move to fun in the website so you can download. So as I said many times, you know, all these techniques, as I said, you were born earlier, you can also invent this. It's not hard. It's move to fun, but it's a research paper called Move to Fun. Essentially, it's like teach you how to jump the cube, jump in fun. So that's what it is. Now, as I said before, the way that we reverse or decode the BWT so far, add the string, sort it, add again, sort it, add again, it's too slow. So there's a different way of doing that, and that way is much faster. We always talk about a better way to do stuff. Now there's an algorithm for that. Again, it's a usual me, I will skip the algorithm. So let's look at the example. And then the algorithm will just make sense to you. Now, this, first of all, if you follow the algorithm, it will create two tables, left-hand side and right-hand side. Let's call left and right. This is left, this is right. So in the left-hand side, what you have is that you have the encoded BWT strings right here, BNN cap AA close cap. Given that we know each other for more than 3 weeks, I'm sure you know that the original string is called banana. There's not that many fruits I like, so you can guess this is banana. But I can tell you the answer is correct, it's banana. But let's say assume that you didn't know it's banana. So we're going to decode that. So there are two tables. the left-hand side and right-hand side. The algorithm will teach you how to create these two tables. Let's do the right-hand side table. It's very easy to construct. So all you need to do is just put down the number of characters. I think it's alphabetically less than the current character. So for example, you just need to ask you, within this character set in the sequence, how many characters alphabetically less than A? 0. Assume that you know the ASCII value of cap is actually higher than alphabet. So 0 character less than A. How many characters alphabetically less than B? 3. Essentially, they're all the A less than B. How many characters alphabetically less than N? Essentially, it's all the A and B together. They're 4. And so on. You can do the rest. Can you do this table? Yes. How long does it take to do this table? You can scan this character once, linear time. You can get this table. Right? All right, good. Now the left-hand side table. What are this? It's also quite easy. I guess you know it's the position. So it's just the position of the character here. 0, 1, 2, 3, 4, 5, 6, and 7. Now, this last column is just telling you how many characters before the current characters that match the same value. As in, how many B before this B? 0. How many N before this N? 0. How many N before this N? 1. How many open cap before this one? 0. How many A before this A? 0. How many A before this A? 1. How many closed cap before this cap? 0. How many A before this A? 2. Can you do the left-hand side symbol too? You can. So now you have these two tables. Decoding is magic. So let's say that you know, because I told you, you need to know either the starting symbol or the ending symbol. There's a special character. Let's say you know the string N with closed cap. You can ask me the question later. What happened? I don't know. It starts with the hash. Then I can answer you later. Let's say now you know that. It closes with the N cap. Then I can tell you, when you close with the N cap, look at two things. Look at this value and that value. Can you do a plus? You can. What's 0 plus 7? You need a calculator, I guess. It's 7. So then you just go to 7. Is the character before. It's A. And A is 2 plus 0. What's 2 plus 0? It's 2. 2 is N. So before that is N. What's 1 plus 4? It's 5. What's 5? 5 is A. So before that is A. What's A here? It's 1 plus 0. 1 plus 0 is what? It's 1. So it's N. 0 plus 4 is 4. It's A. 0 plus 0 is 0. It's B. B is 0 plus 3 is 3. It's cap. It doesn't take you to add and sort, add and sort, add and sort, and add and sort. You can construct this two table. It's a table lookup. You can decode it. I'm sorry. I didn't explain why it works last week. In fact, I will give you more questions by telling you a faster way doing decoding. This is a much faster way to doing decoding. And it will work.
Is there a reason why?
Of course, there's always reason why.
Sounds like magic to me.
Yes. Now, to solve this magic, we need to do something. Well, there's a name for that table. Instead of calling left-hand side table and right-hand side table, the right-hand side table called a C table. Again, you assume someone name it like with a bad naming, but later you know why you call C. Just right-hand side is C. Left-hand side sometimes they call occurrence, which is counting the number of occurrence table or rank table. It's just some technical name. If you read the original paper or some articles or book, they will say this table is called C. This table, some book will call it rank, some will call it occurrence. But they mean these two tables. Try to explain to you then why it works. Need to look at this one. So imagine in the old method, the old method is like you add a column at the end, you sort it. You concatenate with the string again, you sort it. You keep doing this until you get a matrix. When you finish, you will get the n times n matrix. N is the length of the string. Agree? The last column is your BWT. The first column is the same as you sort the BWT. Agree? Or not? First and last column of this. The last column is your BWT. The first column, because you get that by sorting all the rows. So the first column, you sort the BWT, you will get the first column. Am I right?
Wait, but after you sort all these columns, how do you make sure that last column is still the original BWT?
Is it the BWT though? You look at that.
What?
How do you get a BWT? All the rotations, sort them, the last column is a BWT. So what's the difference here? All of them are the rotations, I sort them. The last column is a BWT. How did you get a BWT? All the rotation of the string, sort all the rows, the last column is the BWT. How do you get this in the last step of the decoding? You have all the rotations, you sort them. What's the last column? It's the BWT. The last step of the decoding is the same step of your encoding.
Wait, so it's like applying the BWT to the BWT string? Like, reverse it?
I don't quite get the questions. So the question is it's like applying a BWT to a BWT strings. It's not. I'm just saying that the last step of the decoding is the same step as your encoding, which is because in the last step of the decoding, you have all the rotations. You sort them. The last column, it will be your BWT. And my question in the very early beginning, I was just asking you, the last column is the BWT. You sort the last column. You will get the first column. That's my question.
Oh.
Yes or no?
Okay.
Just look at two columns, first and last. Don't care about the middle one. So it means that anyone give me a BWT encoded string, I sort it, I will get the first column. Yes or no? Yeah, this one is not as nice. I want to show you a nicer one. Maybe this one is nicer. This one's nicer. Have color. So the blue one is a BWT, right? It's the same anyway. It's the same as that slide. This is from encoding anyway. So the last one is a BWT. You sort it, you get the first column.
Yeah.
I know, like you see it, right? It's the same slide. If this one got color, then you see it right away. So. What else you see from this if I only look at 2 columns. As I said, all these middle columns, they are useless for you for now. Just focus on 2 columns, the last one and the first one, because the last one and the first one have some characteristics. It's much easier for you to observe. For example, the first column is all sorted. And the last column is the actual BWT string. Whoever gives you the string, you just sort that string, you get the first column. That's it. Do you have any other relationship that you can find? Yes?
The things are all clustered together?
The things are all?
Clustered together, the letters?
Yes. The letters are all clustered together. Yes. Likely to, I mean, there's some exception, but, you know, most of the time, it will be together somehow. Yes. But anything that is invariant definitely is always true. You find something like, for example, what's always true means like, for example, the first column is always sorted. Do you find anything that's always true?
The first column is always
True. That's good. So what he says, like the first column is always after the last column. Logically, it doesn't make sense. First is always in front of the last. But what he's trying to say is that the characters in the first column is always the character right after the character in the last column. You rotate them. You got it? Means like the letter before B, the letter after B is A. Or the letter before this A is B. That's how you get them to begin with. They are rotation. Right?
Right, it's like a cylinder.
Then you know how it works, the algorithm. It's like, what's the letter after hash? B. What's the letter after B? A. So by looking at their relationship, somehow you can decode the string with these 2 columns. Then, how that table works? How this table works? I'm telling you, this table, the right-hand side table, is like your first column. The right-hand side table will tell you how many A followed by how many B followed by how many N. Essentially, these are the position of your first column. These 2 tables represent your first column and last column. So I can list it like that. This is your last column. This is your first column. And we start with the closing bracket. So what is a letter before the closing bracket? With these 2 columns, how are you going to find it? What's a letter before the closing bracket?
A.
How do you know that?
The first column matches the last column. We find the last one is closing bracket and the last column is A.
That is very good. Because you find this closing one is unique, the last symbol. Closing one is the same as this one. And what's the letter before this one is the last column, because it's all rotation, remember? Okay? So we get the A. Now, the problem with the A, which one is before A? There are more than one A there. How do I know which A? There are 3 A here, there are 3 A there. How do I know which A there is this A? Now I'm telling you that since this is the third A, it will be always the third A there. It's this A. But why? Why is that? You know why this one, first of all, why this A is the third A? Because the letter after this A, which is a cap, is a loser. The first A, the letter before this A, is a winner. When it's sorted it, this first A, the letter after that will be sorted first. It means the letter after this first A here will be sorted first too, when the first letter is the same. It's called all A. I repeat again. You know what's the letter after this A? Is N. What's the letter after this A? Is N again. What's the letter after the third A? Is a cap. So if within this 3A, this one is the last one when it's sorted by the letter after this A, will be exactly the same for this 3A. So their order will be always the same order. You need to think, because if you got it, it's very simple. If you don't, it will be very stuck. It will be always the case from now on for all the algorithm. Once we cover the basic algorithm, the rest of it. For those people who got it, it's a piece of cake. For those who didn't get it, it will be like jumping off the cliff. It will be always like that. You can ask me questions, but we better clear up those. It's the foundation. We clear up those, we can move on. Otherwise, it will be very hard. As I said again, the first A here will be always correspond to the first A there. The third A will be always the third A. For the reason that if this is the third A, means like when we sorted the letter after the A, this third A, the letter after the A will be also sorted as the last one out of these three letters. Say, for example, if the first A is AB, the second one is AC, the third one is AD, that means here will be BCD. And because of that, this here, the 3A will be AB, AC, AD. Their order will be the same.
So, what about the two AN pieces?
Huh?
There are two ANs, right?
Yeah. If this N is better than that N, I'm sure after the N somewhere there will be a value that is smaller than the next string.
Okay.
Otherwise, it wouldn't be sorted like that. So it means like even they all the AN something here, somewhere here the first one is smaller. Otherwise, they wouldn't be sorted like that. It's exactly the same philosophy. Now, this is one of the algorithms, as I said. If you understand everything, it's a very small little thing, it's very simple. But this is the algorithm different than those move to fun or whatever, or Huffman. I was really amazed when I first studied this algorithm. I have no idea why the first guy who invented it found that this trick is really hard. It's small, but it's really hard. And even worse, the guy who found it, like with all my respects, he found it for 10 years. He didn't know that. He didn't publish. He didn't tell anyone. He just thought that he worked it out almost like you guys have nothing else to do at home. Try to figure out that little exercise from Raymond. But after, oh, I got it. I didn't tell anyone at all. And he did exactly the same thing. He just played with it, put it into some scrap paper, keep it for 10 years. One day, told his colleague in a company called Digital Equipment, said, you know what, 10 years ago I found this little thing, I think it's really fun. And then the guy, really? Is that fun? I can't remember who, like BWT, the last one is Transform, the first one is Burrow, the second one is Wheeler. Burrow and Wheeler are two people. I can't remember whether it's Wheeler invented or Burrow related. So the guy who invented tell Wheeler, for example, oh, I invented 10 years ago. I said, really? And they tell me, well, that's really clever. Actually, that's very useful. I said, is it useful? I just bring all the same character together. Is it really useful? I said, of course. So then from the invention to actually being published to the public, there's a 10 years gap. But you would just wonder, what is really, and until he announced that, and we use it for those DNA or bioinformatics search, you search lots of long sequence of DNA. Without that, you won't have the search result today. Most of the sequence search is based on BWT. Otherwise, you would never get the speed and the compression ratio. We will later talk about how we use it for search. But now, we use it for compression. It's the same algorithm. All right, so come back here. Now, as I said, it's not like very hard in a sense that like, it doesn't involve, it doesn't involve multiplication, to be honest. It only involves addition of two numbers. You'll find the position. So it's not hard math. It's not hard algorithm, but the tricks are really, really smart. Now, and how they can bring all the idea of cluster, all the same characters together. The idea is that most of the English alphabet, you have all the likelihood, as in like, if you have A, most likely followed by N, A most likely followed by R, A most likely followed by U, there's some combination. When you see a sensible word given one alphabet, there's a likelihood of the next alphabet. Now, when you put all the alphabet together, for example, if after A is N, no matter where the AN is in the string, after all the rotation and sorting, they will bring together as far as the A followed by the same character. Because when it's sorted, it will be close together. And because of that, you may have a situation like this. The A will not, this last A will not be together with that 2A. It's possible. But in general, when you look at a large file by probability, they will be all clustered together. So this is even more likely. That's why people use it for DNA. The DNA, the sequencing, there's also likelihood the symbol, with that symbol, there's some special bonding, they're likely together too, about the likelihood. So when you sort it like that, they all just come together. So, so this is the idea why it will come together. Now, if you use it on absolutely random character, maybe binary or something, the chance that they will be together is much lower. But if we are talking about a meaningful text information or sequence information with some relationship between characters, the BWT would definitely improve your compression ratio. So continue doing that. This is the third A. We go to the third A. We know there's N, and this is the second N. So we can go to the second N, and then we got A. So we keep decoding. We got A, and this is the second A. So we go to the second A. Then we got N. This is the first N. So we go to the first N. Then we have A. This is the first A. Then we go to the first A. We have B. Luckily, there's only one B. So B will be cap. Now you keep doing that, you can keep going. You know what? You keep going, you just run and run, because the open cap was before the open cap. Before the open cap is a closed cap. Before the open cap is a closed cap. It's just run and run. Question?
So practically, we do not need these square brackets. We only need an EOF symbol. Right?
Yeah, some symbol, some unit symbol practically. But as I said, 2 weeks from now, just keep that. Assume you need it first. 2 weeks from now, you find out you don't even need that. Yeah. But now you need it. Yes. Yeah. It's not hard to implement. So you guys can implement one, and oh, that's BWT. Like all the smart stuff they are not hard to implement. It's hard to understand, but it's not hard to implement. Guess what? It's unusual, but I give you an early break. This early break is for you to have a toilet break and also have a break in your brain so that you can digest a bit. Then you can ask me questions. As I said, I want to clear up all the fundamental questions before I'm going to move on to a bit harder one. So let's do a 10 minutes break and we will resume at 7.
To create the BWT, you still need to sort through all the strings, right? You need to sort all BWT.
For now, yes, but not 2 weeks later. You don't. For now. 2 weeks later, you find that like it's linear time. Okay, guys. Okay. Don't worry. You have plenty of opportunities to discuss. All right. Don't worry. So, don't worry, guys. BWT is going to be with your life for a few more weeks before it disappears. So you have plenty of time to ask questions. Now, just come back to now. So assume that you know how this mapping works. Then we come back to this table again. Now how this table works. This table basically, as I said, the right-hand side table, it captures the first column because it knows where A start, where B start. So you look at here, basically you know A is start from the offset 0. B start from the offset 3. So essentially, this actually captures the starting position of each alphabet in the first column. Agree? Good. Now, we need to know when this is the second A. The second A should correspond to the starting position of A plus 1. Right? That's why we need to know that this is the second A. That's why we have the left-hand side table, that this is the second A, so we need a plus 1. Because we need to know how many A before this A. So this left-hand side table is carefully crafted, or you can say craftily created. I mean, it's like really, the occurrence before is to adjust that this is the second A or second N, so that you can adjust it from this starting position. So that's why if I say I refer to the second A, is the starting position of A0 plus the adjustment of the second A, which is plus 1. So the offset 1. Okay? So essentially, these two tables have no different than this mapping I just showed you. Is to calculate which position of that alphabet in the first column you should map it to. Okay? I mean, otherwise this mapping is good to show, but how are you going to encode it as your algorithm? You can't encode this mapping in the algorithm, so you will do the algorithm, you implement these two tables, and plus the value together, you get the method. You scan this alphabet once, you can compute this number and that number. Yes?
You can do that with, so the left table is just the last column, right?
Yeah, just the last column.
So can't you generate both tables with just that last column? You don't need the first column, right?
The first column? You mean this one?
You don't need the first column.
Well, this is just a position, yeah. No.
No, the sorted, you know, the B and N, A, sorted one.
We don't. We only have these two tables. We don't have, I mean, this one represents the sorted one. This one represents the first column. We are not going to have anything else other than these two tables.
Yeah.
Yeah.
But you know how you said that B and then open bracket AA, close bracket A, you
Yeah.
said the last column.
Yeah.
And you like refer to the first column, how you can sort that string into AAA, B, and then brackets?
Yeah, that's only to explain to you by that. It's only explanation.
Oh, but then you don't need to do
No.
it to generate.
No.
You
No.
don't need to do a sort at all.
You don't need to sort at all, no. No, because by scanning this, as you said, I guess you know what you are saying. By scanning this, you generate the right-hand side table. That is like the sorted one already. That itself is like that.
How do we get that in one pass in linear time? We assume the symbols are limited, right?
All the symbols in this world are limited. If it's an 8-bit encoding, 256. But it's true. We are not doing theoretical data compression here. You assume the size of alphabet is infinite. There's no compression. You can do the alphabet size is infinite. So it has to be finite. So when it's finite, then you create a finite table and do the counting, the bin counting.
Yeah.
That's it. Yeah.
Strictly speaking, you couldn't even represent an uncompressed.
I don't know.
Infinite.
Yeah. So, but anyway, the counting, you talk about just getting to the counting is really fast. Like even you're doing the full binary, 256 of them. Just have a counter, 256 of them, maintain it, and then you can generate. Just one scan. Yeah. So now you solve the decoding problem. It's very fast. The decoding is very fast. Then one of you guys asked me, what about encoding? So before that, decoding is very slow. Now decoding is very fast. Encoding is very slow. Don't worry. Like give us some time. 2 weeks from now, you will have the fast encoding as well. But the fast encoding is much harder than decoding. Much harder. The tricks involved. This is one trick. That encoding one probably involve like 5 or 6 tricks. Each of them will be like that. So it's hard, but it's fast. So, right.
For the decoding, how do you know to start at the closing bracket?
You
And send that across.
you need to know that. So you need to know that. So you need to have a unit symbol. So if you don't know the start with that, you can start with the hash. For example, in this case, if I assume that assume our original example, hash bananas. Then in this case, you can assume that it start with hash instead.
Okay.
Then if you do hash first, then you assume the hash is the last one. Then you end up still get bananas, because it will rotate, as I showed you before. It will just go back and back and back. So it doesn't really matter. Yeah. So far you assume that you know one unit symbol. If you don't know, you can't do it. But as I said, 2 weeks from now, you will find out you don't even need that. But for now, assume that you know one. Okay. I mean, to be fair, if you don't know, pick anyone to start, you just get the rotation itself. It's just one of the string. Right? You pick one of them to start, you just rotate. So it becomes one row in the matrix, one of the row. Right, so there's some crazy people doing dynamic BWT, which I don't think is your cup of tea. We are happy to just stay with the static version. Dynamic means like, you know, the BWT text string, it can be keep coming as a stream, and also like the data may change from time to time. You are not, trust me, you don't want to see it. But if you're really interested, there's a paper. And having said that, I think one of you guys did that. Remember I said that for the assignment. If you think assignments are too easy, you go to project. I think 1 year, one student took that as a project. Result is okay, but I think he rather, he did the normal assignment, as I said. When things becomes, if you know what I'm saying, the difficulty is the same as static Huffman and adaptive Huffman. Then you have the static BWT and dynamic BWT. It's a similar scale of difficulty difference we're talking about. So, but it's very interesting if you're interested. So. All right, guys. Now, if you don't have any more questions, one thing you'll be very happy to hear is we are done with compression. You will see them again, but not learning new compression. You will see them when you need to search the compressed stuff. Then you still need to know, oh, it's compressed, how to search. So then we move on to search. To start with search, some student, when they start this subject, they'll say, oh, I know search. Then I will ask them, how do you know? Well, we learn search from many places, like database calls, information retrieval. Then I'll ask them, yeah, what database search you learn? I say, SQL search. Yeah, that's cool. And then search. How do they do the search? They have a B3 index, like 3 index. But I said, this course is about compression and search. It means like if I give you an Oracle database of 1 GB data, you need to generate 2 GB of index to search. That's not part of this subject. We are talking about how you can search efficiently, means like space not too big. Don't tell me that it takes 1 hour to generate the index I can search in half second, because first I need to pay 1 hour first. That's not what it is. We want to search in an efficient manner, means like depends on the requirement. If you have a requirement that, we have 1 GB of text, and I only give you 200 megabytes of disk space or memory, I want you to compress it, I want to search on it, you have no space to generate index, how? Then you just stand there. So we'll talk about you need to have a variety of methods. So we start with pattern matching without any index. So as in, without generating any extra index, what's the fastest you can search? That will be today. So it's just pattern matching. So the best way you can do is called dummy way. Or, dummy is a bit like not respecting, we call it like, I don't know, brute force is a nicer term, but I call it dummy. So dummy way is like, given a text string T and a pattern string P, which is your search term P. So you try to search for P in T. Let's say T is the ring in Spain, stays mainly on the plane. And you try to search for N with a space TH. Clearly, I can see that N with the plane is right here. N space TH. Now to do this search, what are you going to do? You can do this dummy way, essentially. Brute force is like, when you try to check, it's like, this is a pattern, this is a text. You try to compare the first letter. Are they the same? Not the same. Move on to the next one. Are they the same? Not the same. Until when they are the same, then you check the next character of the pattern, next character of the pattern, and so on. This is a typical brute force way. Okay? Anyone can do that. And what's the worst case of this one? You will know. So what's the worst case? The worst case is like for each of the letter in the T, you need to check all of them in the P until the last one. Bugger. Then next one until the last one. Next one until the last one. So what's the worst case? Very good. Times together. What is the average case? We don't talk about best case. Best case is like bingo, you find it. What's the best case? You buy a lottery? Yeah, you win. That's it. Don't talk about that. You talk about worst case and average. So
I guess it would depend on the distribution.
Very good. So it depends on the distribution. But in general, worst case is M and N. But most searches of ordinary text m plus n, which is actually very good. So in any situations, if you are going to work in a company, they ask you, although I know that these days you don't implement your search because there's so many nice search from a C library, C++ library, Java, so you don't implement it. But I'm just saying that if there's an interview questions, whatever, ask you, oh, just do it. This one, for normal human being text, is quite efficient. It works really fast. So the brute force algorithm is fast when the alphabet of text is large, A to Z, and all the alphabet. When it's large, it's better. Because when it's large, the chance that you will need to check until the last letter of the pattern to reject is lower. You can reject it in the first letter. It doesn't match. Move on, move on. Then you end up, you hope you get m plus n instead of n times n. But when the alphabet size is small, like 0 and 1, there's a higher chance that you need to exhaust the whole pattern until the last letter. No. Then you get m times n. So the smaller set is bad. So you need to search for a binary file, dummy way is slow. So that's the worst case. So R and R. So you search for them. It's bad. So now, but in a normal case, we don't R a lot, then it's good. So string standard to, so so you compare with the A and a store, even the first comparison, you can move to the next one. Space and S, you know that it doesn't match, move on to the next one. So one test on one letter, you can move. So in this case, even the second, even for the string and store, 2-letter comparison, you can move on. So in this case, you are close to m plus n. Okay? So in general, it's quite good. So in a general sense, unless you need to do the search a lot or you have plenty of space, we are not going to build index for normal text search. But can we do better? We can. First one, KMP, from 3 people, Noof, Morris, and Pratt. So we try to look for the pattern in the text in the left to right order, like the brute force, very similar to brute force. But we try to be able to shift the pattern more intelligently so that we can skip some letters if we can, than the dummy one. So if a mismatch happens between the text and a P at the position J, the question is, what's the most we can shift the pattern to avoid wasteful comparison so that we don't need to waste those comparisons again? And the answer for that is it's the largest prefix before the mismatch and the suffix before the mismatch. So the common prefix and suffix before, the largest of them, before the mismatch, that's the best you can do. So give you an example. So we compare 1 comparison, 2 comparison, 3 comparison, until number 6, we found that bad luck. They don't match. So you waste 6 comparisons, you find that they don't match. Then, using the brute force way, what are you going to do? You shift by 1. But we know that already. We know that if they don't match here, and if I look at, first of all, you need to know that the idea when you put in the mindset of the guy who invented this algorithm, he's trying to think of, look at this, stare at this one, and see what's the maximum I can shift this pattern without just shift by 1. I want to shift maximum, but without missing a possible match. But again, you should only look at the pattern. Don't look at the text, because once you try to look at the text, you become a content dependent. You should look at just the search pattern itself. That's easier. So if you look at the pattern itself, you find that, the idea is if the mismatch here, the algorithm thinks that look at the substring mismatch happen in J, look at up to J minus 1. So look at all the matches so far. These are the matches. Mismatches here. These are all the matches. I look at them. I try to look at their common prefix and suffix. It's what? It's A. The largest common prefix and suffix before the mismatch is only A. What does that mean? It means like if I'm going to shift this pattern all the way away from the matches so far, I may have missed a possible A here because I have the A right here. Because the suffix and the prefix are the same, you have to check the common suffix prefix again. You can't skip it. Are you with me? Yes.
What do you mean by suffix and prefix?
So if you look at the string from A, B, A, C, A, the prefix will be A, AB, ABA, ABAC. Those are the prefix. The suffix will be A, CA, ACA, BACA. So you find all the prefix and all the suffix, the common one, if they're the same. What's the maximum, what's the longest common prefix and suffix of this string? Is A. A is a prefix, A is also a suffix. But nothing else in this case, right? So it means like if you want to shift these patterns again, you can only shift the prefix to the suffix position, and we check again because it may have a match. Okay? Good. So now, so then we do the comparison. One thing you will find that if I shift the string such that the prefix shift to the position of the current suffix, do I need to compare again? No, because they're the same. They're the same. Well, when I say the common prefix and suffix means like they're the same value. Of course, you don't need to compare again. That's why after shift this A here, do I need to compare this A with that A again? No, because they're the same prefix suffix, same value. You with me?
Yeah.
Good. So I don't need to compare this again. All I need to do is just compare from the same position that have the mismatch. So, and compare here, B and A. Well, not the same. In this case, there's nothing prefix suffix here because it's only one letter. So I can only shift by one. So I shift by one. I compare again. A, B, A, C, A. All right. So in this case, is there any common suffix and prefix here? No. You are lucky. You win because you can shift with no reservation. It cannot be possible that there's something that you miscalculate. I mean, all of them will not match. Shift all the way. Previously, you can't shift all the way because there's a common prefix and suffix. It might match something from there onwards. So if no common prefix and suffix, that's even better. You just run away. Okay? And start from here. Now, if you look at this one, there's some funny thing. No matter how you skip, your comparison never compare backward. You always compare forward. Because anything that, if they have a common prefix suffix, you do not need to compare again. If they don't have a common prefix suffix, you don't even need to compare them. It won't match. So your comparison always move forward And you can skip a lot when there's no common prefix suffix. You can skip a lot. Yes?
But it still takes a lot of, well, probably not a lot, but some computation. You have to know whether you have a common suffix prefix or not.
Very, very good question. Very, very good question. That's why we will compute. I mean, just to confuse you, because this data structure we copy from the inventor paper. So it's some symbol here, like just to confuse you. In fact, if I explain to you, say, is that all? Yes, that all. So this is just a position. K is just a position of the pattern. So it's a 0 base. So 0, 1, 2, 3, 4, 5, totally 6. 1, 2, 3, 4, 5, 6. There's 6 alphabet in that pattern. You pre-compute what you can shift by the common prefix and suffix here. So what it means is like, if the mismatch is happened at the position 6, which is here, 5. If the mismatch happened here, how much you can shift? It said that you can shift to position 1. It's a 0 base. Means that you can shift to 0, 1, 2. You can shift 1 at this mismatch position. That's what it means. You can shift to 1, the offset 1, into the current mismatch position. If the mismatch happened in 4, which is this A, do we have it here? Here. If the mismatch happened in here, we can shift to position 0, 0 of the pattern. If the mismatch happened here, which will be C, you can shift to position 1, which is B. Why is that? Because the common prefix is A. Right? That's how you calculate this one. If the first one doesn't match, what does it mean? If the first one doesn't match, do we have the first one doesn't match here? Huh? Where? This one? Oh yeah, this one. If the first one doesn't match here, you shift it to -1. -1 means like 0 is next to it. That's what it means. That's how it read this table. Again, I use this representation in case you guys go to read the original paper, I put it there, you know what it means. It's exactly they use in the original paper. So they compute this one for the pattern, and they use it, so it's not so expensive when you're doing the, how much you need to skip. You can just check that number, shift it to that offset. That's it. Now, clearly, you can see that, like here, because there are lots of jumps involved, and we only compare forward, the number of comparisons required will be much less than, in practice, less than a brute force one. Question? This is only for completeness, by the way. We probably don't need to use that a lot in 9319 because this is a basic search. You're supposed to learn it here from data structure and algorithm or somewhere. But I'm not sure they cover or not, so I just go through it again. In case they cover, but not as clear. So we just do it again.
Yeah, it was covered when I did it semester 1 last year.
That's good. So you should all know this. Great. Great, you know that too. You also know that. This one. Did this one cover?
Yeah.
Really?
Yeah.
Okay, then we change the mode, becomes a test mode, and see how good you are. So the test mode will be, which one is better? Since you already studied BM, Boyer-Moore, or KMP, which one's better? You can say depends. That's your usual political answer. Yes?
Can you just go over it again? I did like 197 like 4 years ago and they didn't teach this.
Okay, good. At least there's one audience that want to like. Okay, so until here, You guys got it, right? Cool. All right. So advantage, and it, in general, it runs in the optimal time, which is m plus n. It's very, very fast. Now, but again, if you talk about, sometimes that's one thing practically I don't quite like it. You talk about complexity, we can fool around with each other for the whole semester. All the complexity will be probably m plus n. But what m plus n? What's the actual speed? Because you're talking about this is m plus n, the brute force is probably m plus n, but the number of skips we can do here is much more. So practically, this will run faster. It's not the big O notation. I'm talking about if I time by seconds, this one will be faster because it can actually skip more comparisons. So the algorithm, remember one thing that's very important. There's an advantage of this algorithm. It never needs to move backwards in the input text because it always just compare forward. So this algorithm, you can use it for really large file and even for like some streaming text, you want to do the matching because we never go with the skipping. Even with the skipping, we never go backward. Okay. Now the disadvantage: if the size of the alphabet increase, it's not so well. Why? Because if the size of the alphabet increase, there's more chance of mismatch happen earlier. You don't like happen earlier because when it happens later, if it happens later and it's mismatched, you shift the whole pattern. So you want a mismatch later. Can you see this one? So the difference is like if someone gives you a large alphabet, you are going to use dummy way, probably already quite fast. But if someone gives you a small alphabet, I will use a KMP. So it's a different situation. You choose a different method, you will get totally different performance. So the same thing is like if I give you a large data set and guess what? Then you're going to say, oh, I get a large data set. I have this cool algorithm called KMP I learned from. Don't quote it from my course, quote it from someone else. It's like, I learned it from data structure and algorithm, and it's so cool, I implement it. And you're like, how come it's so slow? Because I know, you use the weapon in the wrong way, this is not the right assumption. So because, I know it's a cool algorithm, but when the size of the alphabet increase, it's not good.
It would, even in the worst case, though, it would basically degrade to being a bit worse than a dummy algorithm, wouldn't it? Because it's going to be a little slower just because it's a bit more complicated to implement.
Yeah, it was just like it won't skip.
So it would be just a bit slower than a dummy algorithm.
And every time you need to check your thing, can you skip? You can't skip. You need to build that too. So it won't be slower than that, but it's slower than to implement that dummy algorithm. It will be faster to implement than that one. Yeah. It's unnecessary. So it's not slower. It won't be slower. So all this skipping algorithm, the worst case will be the same as dummy. But as I said, if I can't use this, I will just use dummy. If I can't use the thing, I will not implement this. Next one. Boyer-Moore pattern matching. It's based on two techniques. In fact, three, but start with two first. So one is looking glass technique, which is finding the P in T by moving backward rather than forward. So you try to match in a backward manner. So you match from a backward manner, okay? So when a mismatch happens, there are three possible cases. So you try to match in a backward manner. So A and A match, of course. Up to the position I and J right here, you try to match X and B. They do not match. So there are three cases.